Hello, so today we're going to look at empirical formulas. I am in your mole packet, and this is page 15, if you want to get that out. So if you have a compound, the empirical formula is the simplest whole number ratio of the elements. It doesn't necessarily tell you exactly what the compound is, but it does tell you the ratio of elements in the compound. So here are some examples. So there's your definition, the simplest ratio. So I could have this hydrocarbon, ethylene, C2H4. Butene is another hydrocarbon, it's C4H8. And then cyclohexane is C6H12. So here's three completely different substances. Yet, if I take the ratio of carbons to hydrogens for each of these, it's a 1:2 ratio. This is a 1:2 ratio. So is this one. There's one carbon for every 2 hydrogens. So the empirical formula for these hydrocarbons is CH2. So again, it doesn't tell me exactly what I have, but it tells me the ratio of elements in the compound. So how do we determine what the empirical formula is? So first of all, we need to know how many moles we have, and then we need to find the simplest ratio of each element. So we use this rhyme. You have this little emoji guy over here singing. We say you take your percent, change it to mass, then mass to moles. You're going to divide by small, and then multiply till whole. And to help remember it, percent to mass, mass to moles, divide by small, multiply till whole. If we were together, we would be saying that together, chanting, singing, until you remember it. Now you can see kids on a test, they're thinking and they remember the steps. They're actually written for you right here as well. Percent to mass, mass to moles, divide by small, multiply till whole. So what does it all mean? All right, so here's a problem. You have an unknown compound, but you find that it has 72.2% magnesium and 27.8% nitrogen by mass. So when you put those two numbers together, it's 100%. There's nothing else in this compound. So it's magnesium and nitrogen, and we want to know the empirical formula. Well, if we're assuming this is 100%, if we started with a 100-gram sample, 72.2% would be 72.2 grams. That's it. We just changed percent to mass. So 72.2 grams of magnesium. And then for our nitrogen, it's going to be 27.8%, or excuse me, 0.8 grams of nitrogen. Now, how do we convert mass to moles? This is what we did earlier in this unit. So we're going to take this number right here and we're going to start a train track. Kind of exaggerated my train track to get it to fit. If I want grams to become moles, I'm going to drop grams of magnesium down here. I know 1 mole of magnesium. I go to the periodic table and I look, it has 24.31 grams. We did these with unit conversions. When I do the math on this, you get 2.97 moles. Let's do it for nitrogen. You have 27.8 grams of nitrogen. You're going to drop grams of nitrogen to the bottom. You're going to convert it to 1 mole. Or using 1 mole equals 14.01 grams. When we do the math here, we get that we have 1.98 moles. Now, a little tip. You need to take these to at least 2 or 3 decimal places. No rounding yet. I went 2 on this example, and that'll work for you. So now I have 2.97 moles of magnesium for every 1.98 moles of nitrogen. Well, you've never seen this before. You've never seen a formula written. I'm going to throw this little piece of paper up here to show you. If I have magnesium, and let me do it in a pen, and nitrogen, we're not going to have 2.97 for every 1.98. You've never seen subscripts with decimals. So we need to, first of all, oh, I think I did that. I wasn't crazy about my wording there, but I can't go back and start over. So I'm going to pick up here. So we're going to take these two numbers. We're going to pick the smallest one, divide by small. The smallest would be 1.98. And we're going to divide both numbers by 1.98. So I'm going to divide this by 1.98. Well, that's going to equal 1. And then I'm going to divide this by 1.98. And that's going to equal approximately 1.5. So I have 1 mole of this of nitrogen for every 1.5 moles of magnesium. Now again, this is where if you wrote magnesium and nitrogen, the mole ratio is 1.5 to 1. We've never had decimals for subscripts, so we need to get rid of the decimal. So we're going to multiply till we have all whole numbers. There's a little cheat sheet down here for you. If it ends in 0.5, you're going to multiply everybody by 2. And in this case, one of them does end in 0.5. So whatever we do to this one, we have to do to this one. So we have 3 and we have 2 here. So now the formula for this is going to be Mg. I'm going to have 3 magnesiums for every 2 nitrogens. Mg3N2 is our empirical formula. Now, if one of these ended in approximately 0.33, 0.34, maybe even 0.31, you would multiply everybody by 3 to give you a whole number. If it ends in 0.25, if your decimal here is 0.25 or 0.75, you're going to multiply by 4. Just remember, whatever you do to one, you must do to another. Okay, I flipped over to the next page. I'm just going to work 2 more examples for you. So in this case, we have 2 elements in our compound, copper and oxygen. Percent to mass. So we're going to start with 88.8 grams of copper and 11.2 grams of oxygen. We're going to start a train track for each. We're going to convert to moles. There's 63.55 grams of copper in every 1 mole of copper. We could do the same thing down here. We're 16 grams of oxygen in every 1 mole of oxygen. So when we work these out, we have 1.397 moles. Remember, you want to take it out 2 or 3 decimals. I went 3 this time. Of copper, and down here we have 0.700 moles of oxygen. So now divide by small. You pick the smallest of these 2 numbers. Well, it's 0.7. You divide them both by 0.700. Whatever you do to this one, you do to this one. And when you divide, you get 1 here. Now, this one is 1.995. That is so close to 2. We're going to round that to 2. So now we don't have any decimal points. We have 2 whole numbers. So our final answer here is going to be copper has 2 moles. So it'll be Cu2 for every 1 mole of oxygen, Cu2O. Copper's a metal. You always put the metal in front of the non-metal in this case. The positive or the cation before the anion. I'm going to do one more example at the bottom of the page here. So sometimes instead of percent, you will have composition by mass, but we do the same steps, except this time we don't have to change the percent to mass. They already gave us the mass. So you have a 0.858 gram sample of some substance that's made of 0.537 grams of copper and 0.321 grams of fluorine. Notice if you add these two numbers together, that's our total sample. So this is actually a little extra information that you don't need. So let's start with our 0.537 grams of copper. Remember the first step, percent to mass, we don't need to do because we already have the mass. And then down here we have 0.321 grams of fluorine. Okay, convert to moles. We have 19 grams of fluorine here for every 1 mole of fluorine. Notice I always put my unit and my substance, 0.0169 moles. Okay, so we did mass to moles. Now divide by small. Pick the smallest number here. So the 0.0085. Well, we're going to get 1. And when we divide this by 0.0085, you're going to get 2. So for this one, we have 1 copper for every 2 fluorines. And I just want to add this number. When you put it in your calculator, you get 1.988. That's almost 2. 1.99, we're going to round that up to 2. So the answer here is CuF2.